Welcome to my videos on Poisson distribution. In the previous three videos, we derived the property mass function of a Poisson distribution from the Poisson postulate. So now we treat the Poisson random variable as the limit of a sequence of binomial random variables. Again, we will use the method of moment generating function. So here I just list the property mass function for the Poisson, which is here. Also the property mass function for binomial, which is here. And later on, we are going to show that this binomial will converge to this Poisson under a certain condition. So this method is kind of different from the previous videos, because now we treat the Poisson random variable as the limit of a sequence of binomial random variable xn. So here's the statement for the theorem. So for a fixed number lambda, non-negative lambda, suppose that xn is a binomial random variable with number of 12, which is equal to n, and also the probability of getting success is lambda over n. So in this case, we need to require that this n will be large enough so that the ratio of lambda also n will be between 0 and 1. So also there's a Poisson random variable, which is here. And then we claim that the xn converts to x in distribution, which is denoted by this notation. So here's the proof. So we only need to show that the moment generating function for xn converts to the moment generating function for x. And any binomial random variable xn can be decomposed as the sum of a sequence of Bernoulli random variable. That is, xn is equal to y1 plus y2 up to this yn, and each yj will be binomial with number of 12 equal to 1, and then the probability getting success p, which is equal to lambda over n. So here again, we need to make sure that this number n will be large enough so that this number p will be between 0 and 1. The moment generating function for Bernoulli random variable is very easy to compute. So by definition, it's given by this formula. And since this yj only assuming two values, either 1 or 0, so it's equal to probability yj equal to 0, and then plus the probability yj equal to 1, and then times e to the tx, e to the ty, with, in this case, this yj is equal to 1. So if you combine these two terms together, and then it's equal to 1 minus p, and then plus e to the t, and then times p. And because this xn is the sum of this IID sequence, so the moment generating function for xn is simply equal to this function, and then to the power of n, so which is given here. So now, just equal to 1 plus lambda times e to the t, and then minus 1 over n. And also, we already know that the moment generating function for x, for the Poisson, actually is given by this formula. And actually, if you do this calculation, and then we find out that it's equal to e to the lambda, and then times e to the t, and then minus 1. So now our goal is to see that whether this sequence, indexed by number n, will converge to this function. And due to the famous equality in calculus, we know that the limit of 1 plus a over n to the power n is equal to e to the a for any number a belongs to the real line. So we know that this sequence will converge to this limit. And because the moment general function for xn converts to the moment general function for x, and then we know that the distribution of xn converts to distribution of x. So let's see a simple example and to see whether this approximation is good enough. So suppose that x is Poisson 5, and suppose that this xn is binomial with n equal to, so this is n equal to 1000, and then lambda over 1000 will be definitely a number which is less than 1. And we want to, so following the theorem 2, we know that this is the Poisson property mass function, and this part is the property mass function for binomial. So we know that these two numbers should be pretty close. So by exact calculation, and then the property that x larger than 6 is equal to 1 minus this summation. So it's about equal to 23.78%. And now we try to calculate this approximation. So this approximation is equal to 1 subtract the sum of this. And we finish that this property is equal to 23.74%. So these two numbers are fairly close. So indicating that this approximation is kind of a good. So in this video 5, we have derived the property mass function of Poisson distribution, which is here, and using the binomial approximation. Also, we use the moment general function to prove this fact. And next, we want to derive the property mass function of Poisson again, but now using a sequence of exponential random variables. So this will be a completely different approach. Thank you for watching.